Hi, I'm Thủy Yun, but you guys can call me June. This talk is the fourth part of the Log-Concave Polynomial series. We will show time mixing time for the Down-up random walk to sample from log-concave distribution using a new tool called Approximate exchange. As application, we show near-optimal quasi-linear time algorithm to sample uniformly from the set of on-site forest. This is the joint work with Nima, my advisor, QQ and Sayang at UW, and Cynthia at NCSU. A direct consequence of our result is the time bound on the mixing time of the basis exchange work on a matroid. Let's remind people about the definition of a matroid. A family of psi k subsets of a gross set of psi n from the set of basics of a matroid if for any B1 and B2 in B and I in B1 but not in B2, there is J in B2 but not in B1, such that when you exchange I for J in B1, you still get another basis. This is called the basis exchange axiom. By the way, such a matroid is said to have rank K, and note that all basis in this matroid has psi K. So we say a subset S of the gross set is independent if it is contained in the basis. So here's a fact: the independent sets of size exactly R from the set of basics of another matroid. So here's an example, graphic matroid. For a graph G, for a graph G, the set of spanning tree of G form the base of the graphic matroid of G. This matroid has rank V minus K, where V is the size of the set of vertices. The independent set of this graphic matroid are the forests of G, and the forests of psi R form the basics of another matroid. So here's the picture of spanning tree and forest. So on the left, the set of edges in orange form a forest of psi 5, and on the right, the orange edges form a spanning tree. So the problem of sampling uniformly from the set of base of the matroid was a long-standing open problem and was only recently resolved by the work of Anari, Liu, Ovais-Karan, and Vincent. And this work won the Best Paper Award at STOC 19. So the random walk they used to sample from the set of base of a matroid was the down-up random walk that I will describe in this slide. So let mu be a distribution over psi k subset of a gross set of psi n. So here in this picture, the top level are the subset of psi k, and the bottom level are subset of psi k minus 1. Top and bottom form a bipartite graph. That's an edge between set S in the top and set T in the bottom, only if and only if T is contained in S. The random walk starts at the set S in the top and then drop one element at random to move to the set in the lower level. So here. Then the walk adds one element with probability proportional to mu of the resulting subset to move back up. So here. And this walk is reversible ergodic and has stationary distribution mu. So for the mu be in the uniform distribution over the set of basics of a matroid of rank K, then Anari, Liu, Ovais-Karan, and Vincent in 2019 showed that this down walk has spectral gap at least 1 over K. This implies mixing time of O of K square log n. Later, Krahengold-Mosa shows that the modified loss overlap constant of this walk is at least 1 over K, and this saves a factor of K in the mixing time. In this work, we saw a tie upper bound of O of k log k for the mixing time using a new tool called exchange inequality. On the result in this slide, applied more generally to any log-concave distribution mu. So we introduced two terms in this slide, log-concave and exchange inequality. We will explain them in the next slide. Also notice that like the mixing time here doesn't depend on this mu star, which is defined at 1 over the minimum probability of the set in the support of mu. And this quantity may be arbitrarily large for log-concave distribution. So our result may be very important in terms of giving reduced bound on the mixing time. Okay, so a polynomial f in z1 to zn is considered log-concave if log of f is concave in the positive orthant as a function in z1 to zn. And the distribution mu is log-concave if its Charity polynomial is log-concave. So here's some example of log-concave distribution. So the uniform distribution over base of a matroid. Another example is the determinantal point process or DPP with respect to a symmetric positive semi-definite kernel L. This is defined follows. So for all subset S of psi k, mu of S is proportional to the determinant of the principal submatrix indexed by S. And note that like for this distribution, mu star defined the previous slide is unbounded. So the spectral gap result and the modified loss overlap constant result by ALOV and CGA are presented in the previous slide doesn't give any useful bound for the mixing time, but our result give a time bound for the mixing time. So. Right, so now let's talk about exchange inequality. So we saw that the, any log-concave distribution mu satisfies an exchange inequality, which can be think of as the quantitative generalization of the strong basis exchange axiom that I mentioned in the first slide. Okay, this is defined, you see the form is very similar. And we also saw that if a distribution satisfies exchange inequality, then the dot upward reaches 2 to the O of k square Worm star after O of k log k step. And so after it reaches this Worm star, then using the MLSI result by Klein and Worm-Mosa, then we will get that the random walk will mix in another O of k log k step. And so our theorem plus the MSI result is enough to prove the time mixing time of O k log k. Another application of this exchange inequality that like certain variants of this exchange inequality imply k to the O of k approximation algorithm for map inference on mu via natural algorithms such as greedy and local search. And this is a generalization of Catharia and Despande in 2016, where they saw like a local search algorithm to perform map inference on certain DPP distribution. So next, let's talk about our main application. We show nearly optimal quasi-linear time algorithm to sample random spanning tree or random forest of all size. So here's some background on the problem of sampling random spanning tree. Anders Broder in the 90s introduced a simple Markov chain for this problem. And then after a long line of work, Stride in 2018 finally saw a nearly linear mixing time. Next, let's talk about the sampling forest problem. So this problem is related to an outstanding contractor, the monotonicity contractor, which roughly say that the edges in a randomly sampled forest satisfy a certain negative correlation properties, as defined here. And in this slide, if we replace forest by tree, so if we sample F uniformly from the set of spanning tree, then the contractor is known to be true. But easy known to be false if we replace forest by like size R forest. So if we only allow F to be sampled from forest of a certain size, and it still remain open for forest of all size. All right, so further, and we held in 92, so that if the monotonicity contractor is true, then we can get a polynomial time algorithm to sample forest. And then very recently, recall that the set of size R forest, the set of size R forest form the basis of a matrix. So apply the previous result. Apply the result that I saw in the previous slide. We get like fast sampling algorithm for mu that is uniformly distributed over forest of a certain size, and then we apply the sampling and counting equivalence to count and sample on-site forest. So this is the first polynomial time algorithm to sample forest of on-site. But the bad thing is this algorithm is very slow because the counting and sampling equivalence introduce a very large blow up in the runtime. So our result for sampling forest and tree can be generalized as follows. So given any weight q wi for I from 1 to n, in O of n log square n time, we can sample from this distribution mu over forest, where like the probability of a forest being sampled is proportional to the product of the weight of the edges in this forest, and then scaled by another factor that's related to the size of this forest. So it's easy to see that like when all the wi are 1, and then when we set like q to be 0, then we get the uniform distribution over spanning tree. And if we set q to be 1, we get the uniform distribution over all side forest. All right, so next let's discuss our technique for the sampling spanning tree result. So recall that a spanning tree are based of the graphic matrix. So naively we can use the dot walk, but each up step can take all of n time to implement, result in the running in a runtime of O of nk, and this is too large. So instead, we use the dot walk to sample from the complement distribution of mu that is uniform over the complement of spanning tree. Then the down step will be equivalent to adding edge to forest, and the up step is equivalent to removing edge. The down step is equivalent to adding edge to the tree, and up step is equivalent to removing edge from the cycle created by the added edge. And the up step can be implemented in amortized or log n time using linked tree. This is solved by Russell, Teixeira, and Francisco in 2018. Also note that like the complement upper forest also form a matrix. So the previous result like give a O of n log n mixing time for this down up walk. So here's the visualization of our algorithm. So yeah, so we add an edge and it creates a cycle, and then we remove an edge. So now let's discuss the technique for sampling forest. Again, we sample from the contaminated forest. The one problem is this distribution is not homogeneous. So far, all our results are for homogeneous distribution. So to fix this, we homogenize this distribution by adding dummy variable y1 to yk. So in this picture, the number of black edge and black dummy node together is n, and the number of orange edge and orange dummy node together is k. So we define the polarization distribution as the distribution over the ground set of edge and dummy node. Here S is the set of black edges and Y is the set of black dummy node, and mu of S cup Y is non-zero if and only if the complement of S is a forest. When it's non-zero, then it's further scaled by a factor related to the size of Y. Note that now this polarization of mu is a homogeneous distribution, and we can apply the Dow of work to sample from this distribution. And this is equivalent to sample uniformly from the set of forest. So here's the visualization of the Dow of work to sample from this polarizing distribution. So removing black edge is equivalent to adding orange edge and vice versa. Also, the same goes for removing black dummy node and adding orange dummy node. So here we add an orange edge. And then that creates a cycle, an orange cycle. Now we need to add a random black edge to this cycle, which is equivalent to remove a random orange edge from this cycle. In another case, we add an orange edge that does not create a cycle. Then again, we can remove an orange edge. And another case is like when we, instead of so instead of like adding a black edge, we add a black dummy node, which is equivalent to we remove a random orange dummy node, and then the orange edge are not affected. And yet another case like now we at the start we remove a random black dummy node, which is equivalent to adding an orange dummy node, and then we remove a random orange edge from the forest. So here's a summarize of our algorithm to sample forest. So we run the following algorithm for n log n step. With probability proportional to 1 minus the size of the forest divided by n, we sample E that is not in the forest uniformly at random, and then add E to F. If there is a cycle C formed in Ft, then we sample F uniformly at random from this cycle and remove F from this from our forest. Else, with probability Q over 1 plus Q, so Q here is 1, so let's just consider this to be 1/2. We sample F uniformly at random from Ft and then remove F from this forest. So here's the visualization of our algorithm without the dummy node. And again, each step of this algorithm takes amortized of log n time to implement using linked tree. And mixing time is O n log n, so together the algorithm takes O of n log square n time. Okay, thank you for listening.